Hi there, and welcome to our lecture on energy. This is Energy 2 of Unit 7. We've got 4 key ideas. First is, what is the relationship between energy and work? Why is potential energy called energy of position? What factors does kinetic energy depend on? And what is non-mechanical energy? So start looking at this first question, the relationship between energy and work. Whenever work is done, energy is transformed or transferred from one system to another system. So if we've got a large box sitting on the floor and we push on that box, we're doing work on that object. And basically what we're doing is transferring the energy from our work to that object. So energy is just the capacity to do work, and we defined earlier work is when we apply a force to an object and it moves some distance in the direction that the force was being applied. So basically it's this energy in order to do the work. And again, energy is measured in joules, same as work was. So work was measured in joules, and so is energy. So there is that connection between those two items. So our next thing is potential energy. Why is it called the energy of position? So potential energy, abbreviated capital P, capital E, sometimes called energy of position because it results from relative positions of objects in a system. For example, we'll use gravitational potential energy here shortly in an equation. Basically, it's where an object is at because of its position. So the higher I hold an object, the more potential energy it has with reference to the floor. So if I hold it lower, then it's got less potential energy in reference to the floor when it falls. We can also have potential energy between atoms. The closer they are together, the more potential they have of interacting and causing chemical reactions to occur. So we can define potential energy, the energy that an object has because of position, shape, or condition of the object. So another note here, if we talk about shape, if we take a rubber band and stretch it out, well, it doesn't matter how high I hold it or how low I hold it, but because I've stretched it out, I've given it a lot more potential energy than when it was relaxed. So any object that is stretched or compressed to increase or decrease the distance between its parts is what we refer to as elastic potential energy. So this is rubber objects like rubber bands or springs. These have elastic potential energies because they can be stretched or compressed. Bungee cords is another one. Any system of 2 or more objects separated by a vertical distance is where we talk about gravitational potential energy. So you're holding a ball up higher. If we let go, it's going to fall to the floor, and it falls to the floor because of gravity. So we call this gravitational potential energy. Another example would be a roller coaster at the top of a hill. Just before it starts rolling down, it has the greatest potential energy. But once it starts its descent, then it is not at its fullest potential energy. And we'll talk about conservation of energy in the next lecture. So not only does gravitational potential energy depend on gravity, it's also dependent upon the mass of the object that you're holding and also the height at which you hold that object. So our first equation for this section, gravitational potential energy, is equal to the mass of an object times the free fall acceleration times height, and we can shorten this to be PE equals mgh. The height is typically a relative term, so basically it's in regards to a reference point of wherever the object's going to end up hitting. So if I hold a ball above a table versus above the floor, when I hold it above the floor, typically it's got a longer distance to travel, so it's going to have a higher potential energy because that height is relative to whatever reference point you have. We'll talk about this free fall acceleration here on the next, or when we do this example problem. So if we have a 65 kilogram rock climber ascending a cliff, what is the climber's gravitational potential energy at a point 35 meters above the base of the cliff? So whenever we're dealing with mass, we want it to be in kilograms. Whenever we're dealing with height, we want that to be in meters. So those are the units we want. So if we had grams, we'd want to convert to kilograms. If we had some other unit besides meters, centimeters, for example, we'd want to convert it to meters before we did our problems. All right, so we're going to list our givens. We've got the mass of 65 kilograms, height of 35 meters, and even though the problem doesn't say we've got acceleration due to gravity, this is kind of one of those assumed values. So just because it's not listed here doesn't mean it doesn't apply. So our free fall acceleration because of gravity is always 9.8 meters per second squared. Sometimes we can round this up to 10 just to make our calculations a little bit easier if we're wanting to guesstimate, just get an idea. But if we're wanting to do the calculation, we're going to use 9.8. And then what I'm wanting to solve for is gravitational potential energy, and again this is measured in joules. Alright, so our equation for gravitational potential energy is PE equals m times g times h. So we're going to plug in the values that we have from a previous slide. 65 kilograms times 9.8 meters per second squared times 35 meters. If we just multiply these units together, we get kilograms times meters squared per second squared. And this as an entire part is going to change to joules. So our numerical answer for this particular example is 2.2 times 10 to the 4th joules. We can move our decimal out, so we get 22,000 joules if we wanted to get rid of times 10 to the 4th. Before we move on to kinetic energy, if you were to do the elastic potential energy, it actually has a little bit different equation than this, but you don't have to worry about the equation at this point. Alright, so kinetic energy. What factors does kinetic energy depend on? Kinetic energy depends on two things: the mass of the object and also the speed that the object is moving. So again, with kinetic energy compared to potential energy, we are concerned about mass, but instead of height or acceleration, we have speed. So just to define kinetic energy, it's the energy of an object due to the object's motion. The object being the mass, and then the motion being the velocity or speed. So we can put this in equation form as well. Ke, which is the abbreviation of kinetic energy, is equal to half of the mass times speed squared or velocity squared. That's why we are going to throw v in here now instead of s. So Ke equals 1/2 mv squared, and that's your equation or formula for kinetic energy. So if we look at the equation on the previous slide, we're halving the mass, but then we're squaring velocity, so then it makes sense to say that kinetic energy depends more on the speed or velocity that the object's moving than the mass of the object. So we have a graph here that shows kinetic energy versus speed, and because it's kind of a sloped upward line, it shows that relationship, that kinetic energy increases more greatly when speed increases. We can also say that atoms and molecules have kinetic energy when they're in motion, which is all the time. Alright, so looking at a math skill problem here, what is the kinetic energy of 44 kilogram cheetah running at 31 meters per second? Again, we want our mass in kilograms and velocity or speed in meters per second. So list our givens. Our mass is 44 kilograms, speed is 31 meters per second, and we want kinetic energy in joules. So we're going to write our equation down. Ke equals 1/2 mass times velocity squared. So plugging in our numbers, we take half of 44, We square 31 and then multiply those two numbers together. We get 2.1 times 10 raised to the 4th power. I should have squares in here too. This should be kilograms times meters squared per second squared, which again just simplifies to joules anyway. So whenever you have work, potential energy, or kinetic energy, you're going to write this capital J for joules. And if we didn't want times 10 to the 4th, we could write it out as 21,000 joules. All right, so we've got other forms of energy. So what is non-mechanical energy? Energy that lies at a level of the atom is sometimes called non-mechanical energy, whereas mechanical energy is the amount of work an object can do because of the object's kinetic and potential energies. This is more on a larger scale of what we can observe and quantify and measure, so that would be mechanical energy. In most cases, non-mechanical forms of energy are just special forms of kinetic or potential energy. We have to treat them a little bit differently. Chemical reactions can involve potential energy. So the amount of chemical energy associated with a substance depends in part on the relative positions of atoms it contains, relative positions, and then how the electrons are arranged around the atoms as well will determine what this potential or chemical energy is. Living things get energy from the sun. We use photosynthesis to turn energy into sunlight, into chemical energy. And then the sun gets its energy from nuclear reactions that are taking place there. So the sun is fueled by something called nuclear fusion, and we'll talk about this later in the semester. Energy can be stored in fields. Electrical energy results from the location of charged particles in an electric field, and when electrons are moving from an area of higher electric potential to areas of lower electric potential, they will gain energy. Light can carry energy across empty space. Light energy travels from the sun to Earth across empty space, and we call what the form is electromagnetic waves. Electromagnetic waves are made up of electric and magnetic fields, so electromagnetic is where it gets its name. So light energy is just another example of energy stored in a field. So we tend to see these electromagnetic waves as visible light, but they do occur as ultraviolet or infrared as well. So thanks for listening.